In this video, we will use Excel to calculate the confidence intervals of exact intercepts on best fit straight lines. We will start with intercepts occurring within the range of the calibration data points, and then we will consider the method of standard additions in which it is necessary to extend the best fit straight line beyond the range of the initial calibration data. We start by comparing the confidence interval of the intercepts for three inks A, B and C. We have three linear relationships of percentage transmission against wavelength for three different inks A, B and C. And their relationships are drawn on this graph with the experimental data for inks A, B and C drawn as three lines, and we wish to calculate the confidence intervals of the wavelength at which each of these lines cross the 50% transmission mark. Initially, in column B, we will perform the calculations for ink A, and we will use the Excel functions for slope and intercept. And so for slope, we identify the known Y values, which are the percentage transmissions, the comma, and the known X values are the equivalent wavelengths. At a later point in the analysis, we will copy data across columns, but we wish to lock the wavelength data to column F, so we will enter a dollar sign in front of the F column. Similarly, we will use the intercept function, again for the known Y's and the known X's, and also with dollar signs. So we now have the slope and intercept of the best fit straight line for the data for ink A, and we wish to calculate the wavelength at which it crosses the 50% transmission line. And to do that calculation, we can use the rearranged straight line equation, which means that we will take the difference between the Y value, which is the percent T in this case, and then minus the intercept in B3, and then divided by the slope, giving a best estimate value of 701.59 at the point at which A crosses the 50% transmission mark. We can now copy this calculation to all the other inks, but we note that in the copying process it has incremented the value of the percentage transmission, so we need to correct that back to 50 in each case. So now we have best estimate values for the points at which these best fit straight lines cross the 50% transmission mark. But the next thing that we have to do is to calculate the uncertainty in each of these values. We start in B6 with the standard error of regression, which in Excel can be calculated by the function steyx, again with the known Y values and known X values, including the dollar signs. We also need to enter the number of calibration points, and we have 8. And now we have to calculate the standard uncertainty, and for that we will enter the equation in the formula bar, and that will be equal to the standard error of regression, which is the uncertainty in the Y direction, but we will divide by the slope to make this the uncertainty in the X direction. We must then multiply by the square root, in which the first term will be 1 over the number of calibration points, which is 1 over 8. And the second term starts with the difference between the y value being measured, which is the 50% transmission in B4, and the average of all of the y values. And we can calculate that directly by average. And these are the average of all of the y values, G2 to G9 in this case. And this difference is squared. This is then divided by, first of all, the slope squared and multiplied by the number of degrees of freedom, which is equal to the number of data points minus 1. And then this is multiplied by the variance in the x values. So we will use the sample variance, and these will be the x values. And again, we will have the dollar signs to lock the x values, giving an uncertainty of 0.38. So this is the standard uncertainty in the horizontal direction. To get a confidence deviation, we must now have the t value, which will be the t inverse two-tailed. The probability for 95-degree confidence interval is 0.05. And the degrees of freedom now are the initial number of data points, but minus 2. The confidence deviation we get by multiplying the t value and the standard uncertainty, giving a confidence deviation of 0.93. So for the confidence interval for A, the minimum value will be equal to the mean value in B5 minus the confidence deviation, and the maximum value will be equal to the best estimate value again in B5, but this time plus the confidence deviation. So this tells us that the confidence interval for the intercept of A at the 50% transmission mark is between 700.66 and 702.53. We are 95% confident that the true value lies within this range. And we can copy these calculations to the other inks, remembering to ensure that the 8 stays as an 8. So now we get the best estimate lambda intercept for every ink plus the confidence deviation in that particular value, giving the maximum and minimum values for each of the confidence intervals. In the method of standard additions, we have a solution that has an unknown quantity of lead, Qs, and this gives a current I of 0.45 times 10 to the minus 7 amps in anodic stripping voltammetry. This gives us our first data point here. The procedure is then to add extra amounts of lead Q and observe the increased current I, giving the XY plot here of I against Q. Assuming the relationship is linear, if we extrapolate the best fit straight line backwards to the x-axis, the distance that we need to go backwards along the x-axis is then equal to the amount of lead in the original solution, i.e. this intercept point will be at minus Qs on the x-axis. The important point in this analysis is that at this large distance from the center of the calibration range, the confidence interval for the intercept opens up considerably, giving a large relative uncertainty in the position of the actual intercept. We will use a simple template for calculating the confidence interval of this intercept. So starting with the data, we have Q, the amount of added lead, and I, the actual currents. So we start with counting the number of data points. It's quite simply 5. We now derive the parameters of the best fit straight line. So we start with the slope, y values, which are the values of the current, and the x values for Q, giving a slope of 0.608. We also calculate the value of the intercept, 0.434. The y value for our intercept on this best fit straight line is quite simply 0. Because we have an exact intercept, we are not using the value of k. We calculate the intercept on the x-axis by using the equation of the best fit straight line, which is quite simply equal to the y value at this point, which is actually 0, minus the y-intercept, the c value, divided by the slope of the line, giving an intercept of minus 0.714. In anticipation of the uncertainty calculation, we also calculate the standard error of regression and the mean of all the y values, which gives the midpoint of the calibration range, which is simply the average of all the y values. And we will also need the variance of the x values, which is the sample variance then of the x values, which are the q values in this case. We will now use the full equation for the uncertainty in x of the intercept, and we will enter this in J4 because we are using an exact value of ys, and this equation is quite simply the value of the standard error divided by the slope multiplied by the square root of 1 over the number of data points, which is in E3, and the distance between the intercept and the mean y value squared, and then divided by the slope squared, degrees of freedom, and then multiplied by the variance in the x values. This gives us an uncertainty of 0.70. We now want a t-value for 95% confidence and n-2 degrees of freedom, which will be t inverse two-tailed with a probability of 0.05, and then degrees of freedom will be the number of data points minus 2, and then multiplying the uncertainty by the t-value gives us the confidence deviation. And so now we can say that the confidence interval is equal to the best fit value of this intercept, which is minus 0.71, with an uncertainty, a confidence deviation on each side equal to this confidence deviation here, giving us a confidence interval for the original amount of lead of 0.71 plus or minus 0.22. In reality, due to the curvature of these uncertainty limits, the uncertainties are not exactly equal on either side of the best estimate, but we will use this confidence interval as our best estimate for this particular problem.